Energy will come to order, and we're delighted to have a terrific panel here this morning. So welcome to our hearing entitled America's Next Generation Supercomputer, the Exascale Challenge. In front of you are packets containing the written testimonies, biographies, and truth and testimony disclosures for today's witness panel. And now I will recognize myself for 5 minutes for an opening statement, followed by our ranking member, Mr. Swalwell. The development and expanded availability of supercomputers has enabled society to push the frontiers of nearly every scientific discipline and accelerate applications of that science in countless fields. It has enabled modeling and simulation necessary to address national security needs. It drives the boundaries of medical research, reduces costs to develop new products, and improves materials design processes, just to name a few. High-performance computing has also revolutionized how the energy sector operates. Advanced modeling and simulation techniques driven by computer algorithms and faster computing speeds improve the efficiency of energy production and consumption technologies. These advancements ultimately trace back to federal investments in basic research that provided the foundation for most of today's computing technologies. From the first megaflop supercomputers of the 1960s, the federal investments have led to push across each landmark 1,000-fold speed barrier to gigaflops, teraflops, and petaflops. I always think of floppy-eared rabbits, and when I was a kid and was showing critters in 4-H, I should have named them Giga, Terra, and Peta, but I just didn't know about it back then because that preceded the first megaflop. Throughout this computing age, we have witnessed yesterday's supercomputers become today's desktop computers and consumer devices, often in incredibly short time frames. The spillover benefits to society are countless and immeasurable. The Department of Energy, led by the Advanced Scientific Computing Research Program, plays a critical role in driving these computing technology breakthroughs. DOE supports world-class computational science facilities, such as the National Energy Research Scientific Computing Center. Additionally, DOE funds cutting-edge applied mathematics research and next-generation networking activities. DOE's next major computing challenge, constructing an exascale computer system that is 1,000 times faster than current world-leading supercomputers, may be the most daunting. Key scientific and technical obstacles associated with the architecture and energy efficiency of an exascale system must be overcome, and an immense amount of resources and effort will be required. As we head down this inevitable path to exascale computing, it is important we take time to plan and budget thoroughly to ensure a balanced approach that ensures broad buy-in from the scientific computing community. The federal government has limited resources, and taxpayer funding must be spent on the most impactful projects. We need to ensure DOE efforts to develop an exascale system can be undertaken in concert with other foundational advanced scientific computing activities. This morning we will hear testimony from expert witnesses regarding how best to achieve this balance. I would like to recognize, if he is here, yeah, he's come in, a leader in this effort, my colleague on the Energy Subcommittee, Representative Randy Hultgren. I would now like to yield the balance of my time to the gentleman from Illinois to summarize the discussion draft of his bill, American High-End Computing Leadership Act.
Thank you, Madam Chair, for holding this hearing today. Exascale computing represents a brave new world of science for our nation. The application of the next generation of supercomputers is vast. A 1,000-fold increase in processing power will give us the intense computing tools necessary to ensure our national security by better testing our nuclear stockpile, revolutionize our understanding and treatment of complicated healthcare problems like neurological diseases or the genetics underpinning cancer with the ability to model new treatments, and ensure our nation's competitiveness in the big data economy of the 21st century by spilling over knowledge and expertise into industry and academia. And while I can postulate further on some of the applied uses of faster machines, I also know that simply by making these investments in basic science needed to overcome challenges in immensely massive parallelism, power management, new architecture, and programming models, we will enrich our nation intellectually and ensure our labor force remains competitive. I think at that point I will yield back, Madam Chair. Let me follow up if I have another minute. Do I?
Mr. Holtgren, you do.
Madam Chair, let me summarize my bill quickly. Thank you. My bill would amend the existing statute by specifying the need to target the specific challenges in power requirements and parallelism required to make the leap to exascale. It would also instruct the Secretary of Energy to conduct a coordinated research program to develop exascale computing systems and require an integrated strategy and program management plan to ensure the health of existing research activities is not harmed. The bottom line is we do not know all of the ways we will use this next generation of supercomputers, but given the vast and unpredictable ways that computing technology has already enhanced every part of our lives, and given the investments being made in other countries to deploy large-scale systems, it's more important than ever that we make this investment today. I look forward to hearing the witnesses, what they think of this legislative proposal, areas we can improve it, challenges that we will face. And with that, I do thank you. Apologize for my confusion here, but I yield back to the chairwoman. Thank you very much, Madam Chair.
The gentleman yields back. And I might add on a personal note, today, my daughter is being awarded her master's degree in digital media from Columbia University. I unfortunately cannot be at her graduation because Congress is in session, but I get to watch it on the computer. So I will get to see it, and I think to myself, first of all, what is a master's degree in digital media? Somebody my age doesn't even know what that is. And certainly when I was her age, I could not have even begun to envision the career that would be open to her as of today. And the career that's open to her as of today is due in part to the investment that the people in this room and that the American people have made in computing for science and for the benefit of mankind. So this is a very important subject. The fact that it is such an important subject leads me to let you all know that there will be several comings and goings by committee members this morning. There are concurrent meetings going around the buildings. In my case, we have the IRS in front of us down in Oversight and Government Reform. And I know there are other members that may have to come and go from time to time. We deeply appreciate your testimony here today. In my absence, our Vice Chair, Mr. Weber, will be in the chair, and of course, Mr. Swalwell, who is our ranking member, who I will recognize now. The gentleman from California, Mr. Swalwell.
Thank you, Chairman Lummis, and also congratulations to your daughter on this achievement. And thank you for holding this hearing today. I want to thank the witnesses for being here. Also thank the witnesses who are not from the 15th Congressional District. We also welcome you as well, but especially welcome Ms. Crawford from Livermore, California. I'm excited to learn more about the work that the DOE is doing in partnership with industry and our national laboratories, including both Lawrence Livermore and Berkeley National Laboratories in particular, and are carrying out to maintain the United States' leadership in the critical area of high-performance computing. As I'm sure the witnesses will all describe in more detail, this capability enables our best and brightest minds to gain new insights into societal concerns ranging from Alzheimer's disease to climate change. Other examples of both industrial and academic research that benefit from our advanced high-end computing capabilities include high-temperature superconductivity to significantly reduce energy losses in transmitting electricity, aerodynamic modeling for aircraft and vehicle design, pharmaceutical development, next-generation nuclear reactor design, fusion plasma modeling, and combustion simulation to guide the design of fuel-efficient clean engines, such as that being carried out at the Sandia National Laboratory's Combustion Research Facility. In short, many of the most pressing issues of our time, whether it's how we find our energy resources, how we make our energy resources more efficient, or how we solve the rising cost of healthcare, can be solved through investments in high-performance computing. A focus of today's hearing is the development of an exascale computing capability. Now, my understanding is that exascale is often interchangeably used with extreme scale to refer to the next generation of supercomputers in general. But it also refers to a computing system that would be able to carry out 1,000,000 trillion operations per second. Yes, 1,000,000 trillion, or a 1 with 18 zeros after it. That's about 500 times faster than the world's fastest computer today. Such a system would be critical to meeting the nation's needs in a number of important research areas like combustion science, climate science, modeling of the human brain, and ensuring the reliability of our nuclear weapons stockpile. That said, as we pursue the next generation of supercomputing capabilities, which I fully support, I also want to ensure that the nation is getting the most bang per buck out of our current world-leading facilities. It is noteworthy that while Lawrence Livermore, Argonne, and Oak Ridge National Laboratories are three of the most powerful supercomputing centers in the world, they are addressing incredibly important scientific issues that really require their advanced computing capabilities. Lawrence Berkeley's National Energy Research Scientific Computing Center actually serves thousands of more users with only a fraction of those leadership machines' computing power. The point is, not every computational research effort requires the fastest, most sophisticated system we can possibly build, and I think we also need to work more to make sure that what's sometimes called capacity supercomputing is more accessible to both the academic and industrial research communities that benefit. I've always believed, whether it was as a local city councilman or a sitting member of Congress, that the government works best when we can share our resources with the private sector, that it doesn't serve anyone any good if we're just doing the research in the government and not transferring that research out to the private sector. And I think high-performance computing, we've already shown in our laboratories, we are transferring it out. The transfer out makes us more efficient, can reduce healthcare costs. Also, more importantly, especially in our area, it can create private sector jobs on top of the thousands of jobs that already exist at our laboratory. So with that, I look forward to discussing these important issues with each of you today, and I yield back the balance of my time.
Thank you, Mr. Swalwell. If there are members who wish to submit additional opening statements, your statements will be added to the record at this point. Well, at this time, I would like to introduce our witnesses. And the fun part today is we have two members here who have witnesses from their districts. So I will start by introducing Dr. Roscoe Giles, Chairman of the Advanced Scientific Commuting Advisory Committee at the Department of Energy and Professor at Boston University. Dr. Giles, and I have that right, don't I, Dr. Giles? Thank you. Has served in a number of leadership roles in the community, including member of the Board of Associated Universities, Inc., Chair of the Boston University Faculty Council, and General Chair of the SC Conference in 2002. He received his PhD in physics from Stanford University in 1975. That's a remarkable record of achievement, Dr. Giles. Thank you for being here. At this time, I'd like to yield to the gentleman from Illinois, Mr. Hultgren, to introduce our second witness.
Thank you, Madam Chair. Our second witness is Dr. Rick Stevens, Associate Laboratory Director for Computing, Environment, and Life Sciences at Argonne National Laboratory. He heads Argonne's Computational Genomics Program and co-leads the DOE's laboratories planning effort for exascale computing research. He is also a professor of computer science at the University of Chicago and is involved in several interdisciplinary studies at the Argonne University of Chicago Computation Institute and at the Argonne University of Chicago Institute for Genomics and Systems Biology. He is doing amazing work at Argonne and at the university, and the entire Illinois community is proud of his contributions to this cutting-edge field of science. We're very glad to have you here, Dr. Stevens. Thank you. I yield back.
Thank you for your attendance today. That was my field, although at a much lower level of academic achievement, Dr. Stevens. We're delighted you're here. Now I would like to yield to the gentleman from California, Mr. Swalwell, to introduce our third witness.
Thank you, Chairman Lummis. And I've been very eager on this committee to have a witness from Lawrence Livermore Laboratory.
I can testify to that.
So I thank you for allowing this witness to be here today. Lawrence Livermore is the largest employer in my congressional district, and I have to really just commend the laboratory for their advocacy of the issues facing Lawrence Livermore. They're in constant contact with our office and this committee. So I'm honored to today introduce Donna Crawford, who is the Associate Director of Computation at Lawrence Livermore National Laboratory. Ms. Crawford is responsible for a staff of roughly 900 who develop and deploy an integrated computing environment for advanced simulations of complex physical phenomena like climate change, clean energy creation, biodefense, and nonproliferation. She has served on advisory committees for the National Academies and the National Science Foundation, and currently serves as co-chair of the Council on Competitiveness High-Performance Computing Advisory Committee, and is a member of IBM's Deep Computing Institute's External Advisory Board. Ms. Crawford has a master's degree in operations research from Stanford University and a bachelor's degree in mathematics from the University of Redlands, California. Ms. Crawford, thank you for being here today, and I yield back the balance of my time.
Thank you, Mr. Swalwell. In my first exposure to Livermore, I used to walk around the lab. My first job out of college was working for a rodeo company in Northern California, and we were putting on the rodeo at Livermore.
It's the fastest rodeo in the world. Did you know that?
You know, considering the rodeo company I worked for, I would believe that. Those rodeos ran like that. And I used to go for walks around the lab just to get some exercise when I was there at Livermore putting on rodeos. So I know where you are. At least I knew where you are when I was a young college graduate in my first job. Our final witness is Dr. Daniel Reed, Vice President of Research and Economic Development at the University of Iowa. Previously, he served as a senior leader at Microsoft, serving as Microsoft's computing strategist to corporate vice president for extreme computing, I love that, and technology policy. He received his PhD in computer science in 1983 from Purdue University. As our witnesses should know, spoken testimony is limited to 5 minutes each, after which the members of the committee will have 5 minutes each to ask questions. I now recognize Dr. Giles for 5 minutes to present his testimony with deep gratitude to all of you for your attendance today. Dr. Giles.
Yes, thank you, Chairman Loomis, and thanks to members of the committee for inviting me to testify today. I think the bill you're considering is very, very important for our field and for maintaining the nation's leadership in computing and computational science. I am testifying today in my role as chair of the advisory committee to Oscar, and I will try to reflect that committee's views of some elements of the Oscar program and hope to demonstrate that we are ready to move forward and sort of eager to move forward in this direction, and it's important that we do so. The Office of Advanced Scientific Computing Research has programs and investments that include computer and networking facilities that support DOE science programs, leadership computing facilities for which the Exascale discussion is very directly relevant, with unique high-end capabilities made available to DOE and to all the nation, including industry. Applied mathematics research, whose results provide the framework for future applications and systems. Computers, science system and software research, whose results both enable applications of current systems and chart the direction for future systems. And beyond this, Oscar investments, Oscar is the abbreviation for Advanced Scientific Computing Research. We get lost in acronyms sometimes. Oscar investments have also built human expertise in the scientific and technical staff at the labs, and through attention to integrating the next generation of computational science leaders into DOE programs and facilities through programs like the Computational Science Graduate Fellows Program, which I also am involved with. It's hard in these few minutes to state the breadth and depth of science productivity that's being enabled by these machines. We now see the beginning of the results of the petascale era. As one measure, we might mention that more than 2,000 peer-reviewed research articles based directly on projects supported by Oscar computing facilities were published in 2012 alone. One I love is a trillion particle simulation in cosmology. Since I started out in the 80s struggling to do a million particle simulation of molecular dynamics, and to go another factor of a million is astonishing. In 2009, our advisory committee was charged with reviewing Oscar's body of work on exascale computing. We delivered the Rosner report, the opportunity, the challenges and opportunities of exascale computing in fall of 2010. We found the case for exascale computing compelling and recommended that DOE should proceed expeditiously with an exascale initiative so that it continues to lead in using extreme scale computing to meet important national needs. As you've heard mentioned this morning, when we wrote that, we were talking about going a factor of 1,000 forward in the future. Now that's a factor of 500. I'm glad to see that we're starting to, in this bill, to really move forward on this. And we've had a sense in the committee that we've been waiting for that forward motion from the system. During this time, Oscar has been busy doing foundational research to make this possible. So and you'll hear more about it, I'm sure, from other speakers, but the establishment of co-design centers, computing research and applied mathematics research, and some prototype projects with Fast Forward and Design Forward that are bringing us in this direction. And I think we're making progress, but not the progress we should be making at the scale we should be making it, and hopefully the bill will help deal with that issue. Our committee has been asked to review Oscar facility plans for the relatively short-term future, the next 10 years, not including exascale deployment, and we found those facility plans to be very sound and compelling that involve enhancements to the petascale systems. We've also recently examined the intersection of big data needs within the Department of Energy and Oscar's exascale program and found them quite convergent. The exascale technologies that we're talking about developing will be essential in systems that analyze big data problems of the nature that come to the Department of Energy from both experiment and theory, and we have quite a long and detailed report about that. I wanted to just summarize by saying I'm very, very glad to see the legislation that we have here. I'm very supportive of the direction we're going. I would only ask that the funding level be sure to be sufficient for the scope of our dreams. Thank you.
Thank you, Dr. Giles. Now I recognize Dr. Stevens to present his testimony. Turn your mic on.
Oh, thanks. Thank you. Madam Chair, Ranking Member Swalwell, members of the subcommittee. I appreciate this opportunity to talk to you about the future of high-performance computing research and development and about the importance of U.S. leadership in the development and deployment of exascale computing. In my own work at Argonne at the University of Chicago, I split my time between trying to advance high-performance computing architectures and systems and doing research on how to do computational genomics in the pursuit of problems in energy, the environment, and infectious disease. And those projects have given me insight not only on the underlying technology, but on the impact of applications. I believe that advancing American leadership in high-performance computing is vital to our national interest. High-performance computing is a critical technology for the nation, and it's also the underlying foundation for advancing progress in modeling and simulation and big data. It serves both of these needs. It's also needed by all branches of science and engineering for forward progress. It's used more and more by U.S. industry to maintain a competitive edge in the development of new products and services, and it's emerging as a critical policy tool for government leaders who can rely on simulations to add insight to policy or technical decisions. Today, the United States is the undisputed leader in the development and use of high-performance computing technologies. However, other nations are increasingly aware of the strategic importance of HPC and are creating supercomputing research programs that challenge our leadership. Japan has significant programs for over a decade in this area. They've fielded large-scale machines that are comparable to the machines in the U.S. But China is emerging as a serious player as well, and Europe has been investing in revitalization of their own high-performance computing sector. So we now have at least 3 sectors on the planet besides the U.S. making serious progress. All have set their sights on the development of machines that are 1,000 times faster than those most powerful machines today. Everyone is looking at exascale. And achieving this goal is important. The drive to exascale will have a sustained impact on American competitiveness. It gives companies and researchers the means and the impetus for developing new processes, new services, and new products. For example, we need increased compute power to enable first principle simulations of materials for energy storage that would give us access to a potential 500-mile battery pack for electric cars. We want to build end-to-end simulations of advanced nuclear reactors that are modular, safe, and affordable. We want to revolutionize small business manufacturing and digital fabrication and put in place a digital supply chain that would potentially revolutionize the economy in the United States. We want to model controls for power grids that have a significant amount of renewable energy. And we want to increase the resolution of climate models to provide more details on regional impacts. And finally, we want to create a personalized medicine that can incorporate an individual's genomic information into a specific customized plan for prevention or treatment of disease. All of these challenges require machines that are thousands of times faster than the current machines. The development of a practical exascale system, however, will also mean affordable petascale systems and broad deployment, broad accessibility. The DOE Office of Science supercomputer centers at Argonne, Berkeley, and Oak Ridge are currently oversubscribed by at least a factor of 3. This means that not all of the science that we could be doing on these machines is getting done. With current funding levels, these systems can only be upgraded about once every 4 to 5 years. And at current levels of research investment, the U.S. vendors are not likely to reach an exascale performance level that we can afford to deploy until considerably after 2020. This is a problem for us if we want to maintain our leadership. Both China and Japan are working on plans to reach the level by 2020 or before. Japan's building a $1.1 billion investment program aiming to deploy exascale machines by 2020, and China's announced a goal to reach exascale before 2020. China is aggressively spending on infrastructure for supercomputing and succeeding in deploying large-scale systems rivaling the largest systems deployed in the U.S. It's widely expected they will regain lead on this capability this year, although their designs are mostly based on incorporating U.S. components. In the future, they plan to deploy systems based on Chinese components. I've been working since 2007 building a plan with my colleagues at the laboratories, academia, and DOE, and we've identified 5 hurdles that we must cross in order to reach exascale. We have to reduce systems power by a factor of 50. We must improve memory performance and cost by a factor of 100. We must improve our ability to program these systems. We must increase the parallelism in our applications, and we must improve reliability. These are not simple tasks, but these are very important if we're to reach this goal. And I believe we have a duty to move as swiftly as we can on this objective. Thank you. I'd be more than happy to answer your questions. Thank you.
Thank you, Dr. Stevens. I recognize Ms. Crawford for her testimony.
I thank you. I thank Chair Loomis, and I thank you, Mr. Vice Chairman Weber and Ranking Member Swalwell, for inviting me to be here today. I ask that my full statement as submitted to the committee be made part of the hearing record, and if I may, I will summarize.
Without objection, so ordered.
I am Donna Crawford, Associate Director of Computation at Lawrence Livermore National Laboratory. I will shorten that by saying LLNL or Livermore. Livermore is a national security laboratory of the National Nuclear Security Administration of the Department of Energy and home to Sequoia, one of the fastest computers in the world. Livermore has the responsibility for maintaining the safety, security, and effectiveness of the nation's strategic nuclear deterrent through the Stockpile Stewardship Program. High-performance computing has been a core competency of the lab to meet this mission need since over 60 years. In fact, the NNSA labs, working in close partnership with U.S. HPC industry, were the forefront of the last revolutionary design shift in HPC computer architectures and applications development. That is the foundation of today's HPC systems. Over the past 20 years, the NNSA labs learned many valuable lessons, including how to best structure R&D efforts to develop computing architectures that meet our demanding mission requirements, while cost-effectively leveraging market-driven technology within industry. These lessons are very valuable in our efforts to develop exascale computing. I applaud the committee for its determined efforts to sustain U.S. leadership in this vitally important and increasingly competitive arena of high-performance computing. It is imperative that the U.S. embark on an R&D program to develop new technologies and computer architectures to support exascale computing. My main point of emphasis today is straightforward. This pursuit must be a joint Office of Science and NNSA effort, working in tandem through partnership with U.S. HPC industry to ensure system architectures that meet Office of Science and NNSA mission requirements. Working together, the Office of Science and NNSA have combined scarce resources and have already initiated a number of R&D efforts and contracts with industrial partners, but lack the resources to invest at the magnitude necessary to assure success over the next decade. Due to the technically challenging nature of developing exascale supporting technologies and computing capability, it is vitally important to ensure that there are competitive teams, each with Office of Science and NNSA laboratories partnered with U.S. HPC industry collaborators. Equally important is the development of an integrated strategy and program management plan. Current U.S. leadership in HPC is a direct result of the nation's investment in computational capability to support the Stockpile Stewardship Program. U.S. HPC investment has provided significant computing capability to maintain the U.S. nuclear deterrent, and this computing capability enables us to simulate in 2D at high resolution and high physics fidelity, or simulate in 3D at low resolution. Today, we cannot simulate in 3D at high resolution and high physics fidelity, which will be required for the stockpile mission needs. Therefore, a new architecture enabling exascale computing is required for the NNSA mission. This will not be easy. Development of exascale class systems cannot be achieved through a straightforward refinement of today's technologies. Surmounting multiple technical issues will be required and will require sustained research and development effort. But there is no doubt exascale computing will yield valuable benefits to near-term mission requirements as well as to U.S. economic competitiveness. Over the last 2 decades, supercomputers have transformed the way the world conducts scientific research and has enabled discovery and development across a broad set of disciplines. In a 2008 U.S. Council on Competitiveness report, the Council states, quote, "Supercomputing is part of the corporate arsenal to beat rivals by staying one step ahead of the innovation curve. It allows companies to design products and analyze data in ways once unimaginable," end quote. In one example, Livermore is leveraging its HPC capabilities in the California Energy Systems for the 21st Century initiative. The California Public Utilities Commission and state investor-owned utilities are collaborating with Livermore to improve and expand energy systems to meet our future energy needs. The owners, operators, regulators, and a joint team of technical experts will use the nation's most advanced modeling, simulation, and analytical tools to gain unprecedented insight and generate new data to reduce risk and inform solutions to issues facing 21st century energy systems, such as renewable energy integration and use of smart grid technology. There are many other examples that highlight the importance of supercomputing and reinforce the value of maintaining U.S. HPC leadership. For now, let me close again by saying thank you, and I look forward to working with the committee to ensure continued U.S. HPC leadership.
Thank you, Ms. Crawford. Dr. Reed, I recognize you for your testimony.
Thank you. Chair Loomis, Vice Chair Weber, Ranking Member Swalwell, and members of the subcommittee. My name is Dan Reed, and I'm the Vice President for Research and Economic Development at the University of Iowa. Thank you for the opportunity to share my perspectives on exascale computing and to respond to your questions regarding the American High-End Computing Leadership Act. Today, I'd like to make 4 points regarding the exascale and high-performance computing program, followed by a set of specific recommendations for the future. They're drawn from my nearly 30 years of experience in high-performance computing as a researcher, as an academic and corporate leader, as director of a National Science Foundation Supercomputing Center, and as a participant in national science and technology policy. First of all, as others have noted, high-performance computing is unique among scientific instruments. It's distinguished by its universality as an intellectual amplifier. New, more powerful supercomputers and computational models yield insights across all scientific and engineering disciplines. Advanced computing is also essential to analyzing the torrent of experimental data produced by scientific instruments and sensors. But it's about more than science. With advanced computing, real-time data fusion, and powerful numerical models, we have the potential to predict the tracks of devastating tornadoes, such as the recent one in Oklahoma, saving lives and ensuring the future of our children. My second point is that we face an uncertain future of computing and in particular high-performance computing leadership in this country. As others have noted, today HPC systems from Oak Ridge, Lawrence Livermore, and Argonne National Laboratories occupy the first, second, and fourth place on the list of the world's fastest computers. From this, one might surmise it all as well. Yet U.S. leadership in both deployed HPC capability and in the technologies needed to create future systems is under challenge. Also, as others have noted, other nations are investing strategically in high-performance computing to advance national priorities. And the U.S. research community has repeatedly warned of the potential and actuality of eroding U.S. leadership in computing and in high-performance computing, and emphasized the need for sustained and strategic investment. I've had the privilege of chairing many of those studies personally as a member of PTAC, of PCAST, of National Academies boards. And yet many of these warnings have been largely unheeded. This brings me to my third point, the deep interdependence of basic research, a vibrant U.S. computing industry, and high-performance computing capability. It's long been axiomatic that the U.S. is the world leader in information technology. However, global leadership is not a birthright. As Andy Grove, the former CEO of Intel, noted in his famous aphorism, "Only the paranoid survive." U.S. leadership has been repeatedly earned and hard fought, based on continued federal government commitment to basic research, translation of that research into technological innovations, and the creation of new products by a vibrant U.S. industry. This brings me to my fourth point. Computing is in deep transition to a new era with profound implications for the future of U.S. industry and HPC. My colleague, Mr. Stevens, touched on many of the issues around energy management and low-power devices, and they are key to this topic. U.S. consumers and businesses are an increasingly small minority of the global market for mobile devices and for cloud services. We live in a post-PC world, as we all know, where U.S. companies compete in a global device ecosystem. Unless we're vigilant, these economic and technical changes could further shift the center of enabling technology R&D away from the U.S., with profound implications for our future HPC capability. Given this, what are my recommendations for the future? First and most importantly, we need to change our model for HPC research and deployment if the U.S. is to maintain its leadership. This must include deep and sustained interagency collaborations defined by a regularly updated strategic R&D plan and associated verifiable metrics, commensurate budget allocations, and accountability to realize the plan's goals. DOE needs partners. It needs the National Science Foundation, the Department of Defense, NIST, and NIH, and other agencies to fulfill their important and complementary roles to DOE as engaged partners and supporters of basic research and technology development. We also need long-term industry engagement. Second, advanced HPC deployments are crucial, but the computing R&D journey is as important as any single system deployment. A vibrant U.S. ecosystem of talented and trained people and technical innovation is the true lifeblood of sustainable exascale computing. Finally, we must balance and embrace dual-use technology R&D, supporting both high-performance computing and ensuring U.S. industry competitiveness. Neither HPC nor big data R&D can be sacrificed to advance the other, nor can hardware R&D dominate investments in algorithms, software, applications, and people. All are crucial. Finally, let me again commend this committee for its continued commitment to high-performance computing. It's been my privilege to testify here many times. I appreciate the support of the committee, and like my colleagues, I'd be delighted to answer questions at the appropriate time.
Thank you, Dr. Reed, and thank you all for your testimony. Man, lots of questions come to mind. And, you know, I guess I'm an old-timer. I grew up back in the 60s, and we didn't have computers in high school. Well, actually, we did. There was a flat table. You put a quarter in, and you chased a little Pac-Man around. Those were our computers. So I have a question here, and I think you kind of alluded to it, Dr. Reed, but I'll ask this maybe starting with Dr. Giles. Is it Giles?
Giles, actually.
Giles, there you go, thank you. In December 2011, Congress directed the DOE to provide a strategic roadmap relating to the development of an exascale computing system. However, it's my understanding that after 15 months of the mandated completion date, the report is not yet finalized. Are you aware of this report?
I am aware of it, but my position is as an external representative of the community relative to Oscar, so I'm not actually an insider, and I have not seen the report.
Okay.
It is my understanding is exactly what you said.
Okay.
But I don't have anything, unfortunately, to add to that.
Nothing that you want to admit here publicly, huh?
No, actually, nothing that I know.
No, I'm just,
I mean, I'll anything I know, I'll tell you.
well, of course, our goal is to get to the Dr. Stevens. How about you?
Well, I'm aware of the report. I think it's a fine plan. I think that the internal process of getting that report out is what's blocked it, and I hope it reaches you quickly.
Okay. Any help you can give us in that endeavor?
I don't have any specific recommendation except to just reemphasize that this is a critical plan that must be delivered and must be understood and articulated and executed.
Okay, thank you. And Ms. Crawford, I don't mean to put you on the hot seat, but you're on the hot seat.
I have nothing to add to what Dr. Stevens said. We work at the laboratories, and we're not part of the formal process between the DOE and the OMB to get that report out. I do support what's written in the report. The lab's had a lot of input. I have not seen the final report.
And Dr. Reed, since you came to us with 4 points followed by recommendations, and I love that, by the way, one of the things you said in your recommendation was the Department of Energy needs partners in long-term industry engagement. How do we expedite this? How do we make this happen?
Well, I think there are several points relevant. One is to recognize that, as I said, it is a false dichotomy to pit investment in some of these big data issues against high-performance computing. And I think, frankly, that's the root of some of the issues that we have to resolve in terms of moving forward. In terms of the agencies, I believe, as I pointed out in my written testimony, that they each fulfill and historically have fulfilled important and complementary roles. The Department of Energy has been crucial in terms of advanced prototyping and deploying of the largest scale systems. The other agencies, though, provide support for enabling technologies research. The National Science Foundation is one of the key enablers of that long-term research. What's important is that all those players be at the table and be engaged in supporting this integrated agenda. I think from the industry's perspective, sir, to answer your specific question, that's where industry, and I speak now again from my industry experience, it's important that the government be a committed and not fickle partner, because the cost of money and the time planning for companies to execute is really crucial. And as I was saying, that combination is key to the future of the U.S. industry, not just for high-performance computing, but for how much information technology means to the U.S. economy.
All right, thank you. And Ms. Crawford, let me come back to you. I think you said that this exascale computing won't either can't or won't be achieved through refinement. What do you mean by that?
What I mean by that is that current system architectures today can't simply be scaled up to produce a usable and cost-effective system. In principle, one could scale it up and you would have a system that would fill the room and would take 100 megawatts of power, so that's not a cost-effective system. So the technologies have to change, and we have to change in memory, in processors, in storage, and networking, and the programming models. And so that's what I mean by we can't simply scale up the programs
so
of today.
Let me jump that over to Dr. Stevens. You mentioned about more or less power, I guess. Explain. You said less power.
Right. We need to develop processors and memory and network components that consume considerably less power than current systems in order to scale up. Right now, if we took a current kind of 10 petaflop system and scaled it up to an exascale, it would consume nearly a gigawatt of power, which is not feasible from a physical infrastructure standpoint or a cost standpoint. So we need much more power efficient devices. We also need better programming models, because we're going to have a lot more parallelism inside these machines, 1,000,000 or 1,000 times more parallelism than we have now. And we need ways of accessing that parallelism easily for programmers. So we have a lot of work to do. We know what to do. The DOE's plan includes all of these activities. So I think the U.S. has a good position to do this. We just need the resources and the long-term commitment.
All right, thank you. And I just want to make an observation before I yield to the ranking member, and that is that I'm glad to hear you say that national security is involved in this and tied up in this. That's very crucially important. I think that will carry a lot of weight with Congress. Hopefully it will. So thank you for your testimony. And with that, I yield to Mr. Swalwell.
Thank you, Chair. And thank you, Mr. Chair. And my questions will principally be for Ms. Crawford. First, does research in high-performance computing require the United States government to make investments? And what I mean is, why can't we simply rely on the private sector to innovate and invent the next supercomputing architecture and software, and then the government can just buy off-the-shelf technology?
The short answer is yes, the U.S. government does need to invest in order to shape the exascale architectures for our mission needs. I can use an old example. When we started the Accelerated Strategic Computing Initiative in the mid-1990s for the Stockpile Stewardship Program, industry and the consumer base was driving computing in a direction that would not meet our needs. And without our investment, on our sustained investment and focused on cooperation and developing those processors that would meet our needs, we wouldn't have had the computers and the computing capability that we have today. And so today, it's essential that we work together with the Office of Science Laboratories and the NNSA laboratories to meet this mission needs. A shorter answer, perhaps, is that we're going to follow industry technologies. We can't afford our own, brand new fab or our brand new machines. What we want to do is pay on the margins to make those machines viable for our particular applications, which is mimicking the physical phenomena around us.
And when we look at our global competitors, Japan, China, India, Brazil, Russia, are they allowing or relying solely upon the private market, or are they also having government investment and government at the table as well?
There's strong government investment in Japan, China, Russia, the European Union. There's about $1.1 billion of investment in Japan. I would have to do the translation, but the most five-year plan within China is investing, and again, not just in the hardware technologies, but they're investing in the low-level software and the applications and making sure that they have the ecosystem in order to be able to deploy these systems effectively to make a difference to their underlying national security and economic competitiveness. So they're making large investments.
It sounds like for the U.S. to keep its edge in high-performance computing, we will need to continue to have the federal government make investments in these programs. Is that right?
Absolutely.
You talked a little bit about the joint partnership that must take place between NNSA and the Office of Science. Why is exascale capability so critical to DOE's National Nuclear Security Administration?
So then I will take a more focused view on just what's going on within the NNSA laboratories. It is our duty to assess the state of the stockpile on an annual basis. And the stockpile is being decreased in the numbers of weapons and the types of weapons. That makes each single weapon remaining in the stockpile critically important to understand what's going on.
Going toward a more leaner and meaner model.
Right? Leaner and meaner. And so those systems, as they age, they are being modernized as parts begin to fail. And so there are a number of things that we need to understand physically. Nuclear weapons are very complex. Think about parking your car in the garage and not turning it on, but then wanting to be able to use it when you have to. There's special materials that are changing over time and rings that outgas and all kinds of things that go on just sitting there. And we need high-fidelity 3D simulations to understand the initial conditions, the engineering features, the safety features, the security features. And today we cannot simulate at that high fidelity. So we have a number of what we do is look at the kinds of calculations we're going to do and the kinds of computing that is required to do those calculations. And so for stockpile assessment, for the life extension programs, for materials aging, for safety and surety, we have a range of exascale needs for the kinds of calculations that will have to go on in high fidelity, high resolution 3D. And they range from half an exascale to 1,000 exascales over the period of the next 10 years.
And Ms. Crawford,
starting in about 2018.
Can you tell me more about Livermore's work to address industrial and medical research needs? For example, your groundbreaking simulation of the human heart and your recent work with the California Energy Commission to improve energy management throughout the state, and how Exascale and HPC have affected our ability to do this?
I'd be glad to. Having developed these capabilities for our mission drivers, then they are applicable, as Dr. Reed has said, to many other activities. Last year, we worked with IBM to develop a code called Cardioid, and it models the electrical signals of the heart, and it has the potential to be used to test drugs or medical devices. The code ran in nearly real time across our 20 petaflop machine at Livermore, beating at astonishing 60 beats per minute. So this is almost 12% of real time. This calculation ran at 59% of peak of this machine, and it's very incredible and amazing thing to take a new code and put it on a new machine and run at this scale. It runs in time to solution over 1,200 times faster than the previous state of the art. And this work shows promise for what advanced computing can do for understanding the human body. But it also demonstrated the extreme level of specificity and technical acuity required to achieve this result. And of course, these insights that we gain there will then be applied back to the stockpile.
Great. Well, thank you so much, Ms. Crawford, and thank you again to our other witnesses. Thank you, Mr. Chair.
Thank you. And I will recognize myself for 5 minutes for a few questions. Part of our challenge as a subcommittee is certainly to understand the right thing to do, but also to present it to the larger committee and even beyond that to members of Congress. So a couple questions just of even messaging or how to present how important this is and why this is so important. So I would address this first question to Dr. Stevens and Ms. Crawford. I wonder if you could just discuss the expected breadth of applications for the Exascale computer. Is this something that could be used for a wide range of important disciplines, from material to chemistry to medicine to nuclear science, similar to current supercomputers, or is it expected range of disciplines more narrow, such as climate science modeling or for weapons development?
So the range of applications for Exascale are no less broad than the current machines. In fact, there are many problems that haven't been tried in the past, particularly in biomedical science, where we were just afraid to try them. We didn't have enough compute power. This idea of trying to build, say, detailed models in the human body, not just the heart, but now include the lungs, include the nervous system, include the gastrointestinal system, and build a virtual human, that's a problem that will require 1,000 times current machines. It's not really feasible, so people haven't tried it. So my sense is that we will find more and more applications as we build more capable systems. We're also going to increase the ability for these systems to deal with data. And so a new class of applications that's emerging in both national security and in engineering research is this idea of doing modeling and simulation with uncertainty quantification. This idea that not only will you get a result, you will get some confidence measure on that result. And that's something that requires hundreds of times more compute power than the current capability, which means you can only do one simulation.
I second everything that Dr. Stevens said, and it's limitless. Computing is so foundational. Any physical process that you can represent mathematically, which are most of them, you can then model in the computer with great fidelity. And the greater the fidelity we have, the better we can understand the world around us. And so I can just go on and on and on, but we work at our laboratory in a number of areas with industry, with other national laboratories, with academia, to make sure that we are applying these to the breadth of possibilities.
Well, Ms. Crawford, if I can get into just a little bit more specifics and really following up on the ranking members' discussion and also on the vice chairman's of what does speak to members of Congress and inspire us to make a commitment, especially a financial commitment at a time like this, and certainly one of those is national security. So wondered if you could just talk briefly, is Exascale Computer considered critical to advancing national security? And if so, has the National Nuclear Security Administration gone on record to say that? If so, how is the NNSA prepared to financially contribute to this effort, and what would be an appropriate percentage contribution to an exascale computer from NNSA, would you say?
There's a lot of questions there,
Yeah.
so let's see if I can remember them.
First thing is, have they gone on record of saying that this is a key component? And then basically then, what kind of commitment should we expect from them?
Computing is the integrating element of maintaining the safety, security, and reliability of the nuclear weapons stockpile without returning to underground test. So by integrating element, what I mean is we have the old test data, we have above ground small experiments that we are doing, and we have a lot of theory, and we have our new models, and we are bringing this all together in the computer. So this is an integrating element, and this is the only way that we know to understand what is going on in the nuclear weapon. And so for that reason, we believe it is extremely important. The NNSA is making an investment in the Advanced Scientific Computing Program. To maintain leadership, you need to have a base program. You need to have sort of a near-term program, and you need to have a far-reaching program. Currently, the Office of Science and the NNSA both have a very strong base program. We've heard about the wonderful facilities at the laboratories, and of course it's not just the computer hardware itself, but it's the applications that help us understand the world around us. We are investing with the Office of Science in some near-term research with industrial partners to look at some of those long lead time technology changes that need to be made. We need to make additional investments that are not in our current budgets in the programming environments for the exascale computing and in the math libraries so that we can actually use this billion-way parallelism.
I see my time has expired at this point. I hope that we'll have an opportunity to have a second round of questioning as well. We can talk about that. But let's go ahead and we'll recognize Mr. Vesey from Texas. Okay. Then Mr. Lipinski from Illinois is recognized for 5 minutes.
Thank you, Mr. Chairman. I wanted to ask everyone on the panel question about international partnerships. Obviously, this cuts both ways. You can reduce the cost of reaching exascale capabilities with international partnerships, but then there's the issue of damaging our nation's economic competitiveness, potentially, or national security, because we are not doing this on our own. Now, where do you come down on this? Is it worthwhile, and how far should we go in international partnerships? At what point is it still an advantage? At what point does it become a disadvantage for us economically, giving up our lead on high-end computing? So whoever wants to start with that one, Dr. Stevens.
I'll start. So I think the primary opportunity in international collaboration is in software, and in particular the components of software that are open source. That right now most of the software that runs on these machines, other than the applications, is built based on open source technologies developed largely in the U.S. That's a significant lift to move all that software to next generation platforms, and international collaboration can help there, provided that the software stays in the open. Okay? I think where we don't want to go, at least in the near term, is in deep hardware partnerships internationally. I think that's a place where we want to maintain our competitive edge. We have significant advantages with the U.S. vendor community, and we want to maintain that as long as we can.
Thank you. Anyone else? Ms. Crawford?
Yes, I would like to add that it's very important that the United States maintain the key intellectual property for the next supercomputer levels. If we control that, we have the high ground for the standard space that will make all the decisions in the coming decade. And I would not want to cede that to another country. I cannot trust the U.S. nuclear weapons technology to a system built in China, say. That's untenable. I would like to not consider that those low-power technologies are developed ahead of time in other countries that we will use embedded in our intelligence systems. To me, it's very important that the U.S. take a very strong leadership position in this technology arena.
Thank you. Dr. Reed?
Yes, if I might add to that. It's part of the reason in my testimony I spoke very specifically to the importance of U.S. industry engagement. And as we move into this increasingly mobile device, low-power world, which is one of the key enabling technologies for future exascale systems, it's really crucial that the U.S. vendors maintain the competitive edge and strike a balance, as we do in terms of investment, between the global market and maintaining unique capabilities for U.S. national security. And that's part of the role of the federal government in terms of, as Ms. Crawford said in her testimony, about shaping the direction of industry to ensure that we have the technology capability that we need. And I would echo that there were other uses as well, as we've talked about the rise of data analytics and its importance for national security and signal intelligence and other domains. That's another area where we must think carefully about many of the enabling technologies, of which hardware is one, but the algorithms and other pieces need careful scrutiny also.
Thank you.
Yeah, I would agree with what's been said. Just 2 points. I think it would be truly shameful for us to give up the elements of leadership that we have. I mean, one of the things we pointed out in the ASCAC Exascale report was the criticality of time and of seizing the opportunity that in some way is presented uniquely to us to advance this field. But many, many countries will want to do that. And we have a little bit of a time advantage because of our starting place. The other point, which is it goes sort of in the direction of the open source software, is the observation that a lot of the open science that's done in the world is done with international collaboration and with international connections. And we would, I think, like to still be in the position of having a lot of influence on the underlayer of that, on which we will all build. But there certainly is international collaboration in science, and I wouldn't want to minimize that, the importance of that for the open science community.
Thank you very much. And I won't ask a question if Chairman will give me a few extra seconds there. I just want to also echo what I know some of my colleagues have stated. I know exascale computing is important, but we have to make sure that we don't pursue that at the expense of other important R&D activities that Oscar is doing. That I'll yield back.
Gentleman yields back. I will go through a second round of questioning if anyone would have other questions. So I will begin by yielding, recognizing myself for 5 minutes. And I would address this first to Dr. Stevens, but also ask if any of you would have other thoughts on this, and really following up on Mr. Lipinski's questions of timing and competitiveness. And wonder, Dr. Stevens, if you'd have some thought of what level of investment is needed for U.S. to maintain global leadership in scientific and technical computing for the next decade. And then something specific of if we maintain current investment, at what point would China surpass us in computing capabilities? And then also just looking at dates, what type of approach and how much investment would be necessary for us to lead to a deployable system by 2020?
Okay, so on the first one, in terms of the resources required to do this, in the plans developed by the laboratories, we estimated that in addition to the current funding levels that we have, we would need an increment over time of approximately $400 million a year. That would be split between the two partners, the Office of Science and the NNSA. At that funding level, we think it's feasible, not guaranteed, but feasible to deploy a system by 2020. Of course, we made those estimates a few years ago when we had more runway than we have now. And that investment would go to both hardware and software and some applications, although more applications work would be needed by that time. At the current funding level, not including the bill that's in front of us, it's estimated that we would not reach an exascale capability until middle of the next decade. We don't have accurate estimates of precisely what China will do, but my guess is they will probably exceed us by the end of the decade if we were in that scenario. I don't remember your.
I think that covered it. So really it is, if we can, without the investment, it's going to be probably 2025 before we'd reach that level.
Absolutely.
You think with the investment, do we have is it a possible expectation to reach exascale levels by 2020?
I think it's possible. I think we would have to get moving faster than we are now. And of course, the industry is ready to do this. Labs are ready to do it. Academia is ready to do it. We just need the resources and the commitment, and also to do it in a way that doesn't cannibalize the current program. We need the base. We have to build on the base both in the Office of Science and in NSA. And so this is really looking at incremental resources, unfortunately, to do it.
Okay, thank you. Do any of the others have any thoughts or disagreement?
I would just add that understanding what the sustained commitment is, whatever that dollar level turns out to be, is critical, because then we can plan into the future. And not knowing whether the base budget is cut and the exascale R&D budget is cut, and we've got a commitment to do this, and now we must do that because we have a contract, and yet that prevents us from doing something else. So not knowing is really difficult to plan ahead and manage it effectively. So understanding that and sustaining that is very important.
Yeah, I absolutely agree, and it's one of the things I'm passionate about. I know other members of our subcommittee and committee are as well, of bringing some certainty, specifically to research and to science. When we are looking to advance these programs, it's so important that we're not budgeting month to month, which this place, Washington, D.C., has kind of fallen into the habit of doing, but it has an incredible detrimental impact, I know, on the great work that you all are doing. So I, for one, and I know my colleagues on both sides of the aisle would love to see some of that change. We're going to be fighting for that. Let me switch gears just a little bit and address this to Dr. Giles, if I could, and also to Dr. Stevens. But with respect to achieving an extraordinary number of computations per second, exascale appears to be a somewhat arbitrary goal. With current budgetary constraints, could DOE consider slower systems that would still be by far the fastest in the world? Or how do you see that fitting into this challenge of kind of keeping up with the rest of the world? If DOE were to say, well, we want to do some advancement, but we're not going to go for that larger goal, we'll just kind of settle for a lesser goal. How do you see that impacting the work that you're doing and the work that other nations are doing?
Okay, I think the key research to lower power consumption, to identify the pathway that takes us to exascale, is one that is defined by that goal, but which is a sort of has a certain integrity of its own. Okay, if you do that, if one does that and makes that commitment to do the research and to do that beginning development, then how far you take it is part of the deployment question of how big a machine you build with the technology that you've done the research for. So at least that's my take on it. I'm not the technologist that Rick is, and you may have a comment on that.
Well, what I can say is that the laboratories are excellent stewards of the nation's money, yes, and we will buy the most capable systems that we can afford to buy when we have to replace and when we can replace the current systems. So I think the question of can we settle is really a question of, do we want to settle for not being able to do all the science or the most impactful engineering or address the most important national security challenges? We will do the best we can with what is provided to us. There's no question. I think lowering our sights, though, is not in our DNA.
Right. No, that's helpful. Thank you. My time has expired. I will recognize the ranking member, Mr. Slawell.
Thank you, Mr. Chair, and I appreciate your comments about providing more certainty to our national laboratories. And we know that it's not just the laboratories who need the certainty, but also private industry or any contractors who depend on work from the laboratories. One of the first lessons I learned when I was a planning commissioner years ago on a local sign ordinance issue from a local small business owner was vote for me, vote against me, but just give me certainty, and do not have month-to-month sign regulations that give us no certainty at all, which now I've learned here, as the chair said, month-to-month budgets also don't serve our laboratories well or private industry well. And so I join you in hoping that we can find ways to provide more certainty. I was hoping to just go witness by witness briefly, and if you could just tell me for my own edification, and I'm sure many others are curious, what are the private-public partnerships that you have at your laboratories through the Exascale program?
Well, let's say I don't run a laboratory as
Sure.
some of the others do, but I would note things like and Rick, you do run a lab that does this, the Insight program in Oscar that invites researchers from outside DOE and from industry, and with a particular emphasis on some industries, to use the most advanced facilities that we have. So I think that would be one that I would identify coming out of Oscar.
Great. And Dr. Stevens?
Well, just a few that we've done in the recent past. We've got a collaboration with Pratt & Whitney developing more efficient turbine engines, with Procter & Gamble on a variety of improving consumer products, with the Cummins in improving diesel engines, and Caterpillar improving their ability to model whole vehicles, and including the transmission systems and so forth, with the Mayo Clinic in applying computation to large-scale problems in metagenomics, and so on. There's a long list. Some of these are collaborations with end-user companies, and some are collaborations with companies like IBM or with Intel and with Cray in developing next-generation technologies. And we also work with small businesses. So the laboratories have collaborations on both the end-user component of this technology and the companies developing the technology itself.
And when I hear some of those companies, IBM, Intel, Cummins, Caterpillar, I think of billions and billions and billions of dollars of exports. Those are some of the largest exporters in the United States. And if we are going to truly achieve our goal of doubling our exports over the next 5 years, making sure that those companies can continue to play a part in reducing that trade deficit we have, about $40 billion every month, is crucial. And it sounds like the laboratories are helping them to do that, so they can sell their goods and services to the marketplace outside the United States.
Absolutely, and we're also working with companies like Dow and DuPont and Johnson Controls, and it's a long list, right? And I think we exactly get this idea of helping American industry be more competitive.
Great. And Ms. Crawford?
So rather than going through the long list, let me talk about the barriers for industrial adaptation of advanced computing. There have been a number of studies, and there are three main barriers. One is the cost of establishing a supercomputing facility, the computer itself, the computing room, etc. The second one is the expertise, having the skilled workforce that understands how to use these computers in a meaningful way for their product. And then the third is the software itself that helps them understand their products and how to improve those products. So the kinds of partnerships that Dr. Stevens is talking about and that we have at our laboratory are helping to demonstrate to industry how to overcome those barriers so that they can, in fact, utilize this. And once they have firsthand demonstration and know the value, then that they will start making the investments themselves at a higher level to drive their own productivity and competitiveness.
Great. And Dr. Reed, also just like Dr. Giles, I know you do not run a laboratory, but any public-private partnerships you're familiar with that are working right now and also helping the innovation economy?
Certainly, and I've been in similar roles in the past. As I mentioned, I used to run an NSF Supercomputer Center, and we did very similar things in Illinois when I was there. Advanced manufacturing was certainly a target, logistics and supply chain optimization. At Iowa now, there are many issues around advanced biological modeling. Now we think about the future of healthcare in terms of everything from modeling the characteristics of lungs and what the implications are for drug delivery, how we might work with companies about those issues. I would echo what Ms. Crawford said, though. What's really crucial in those engagements and use of high-performance computing is simplicity of use, because the domain experts are interested in advancing either the technology or the science or its applications, and less interested in understanding what those of us in the technology business might view as the really cool stuff. Right. It is a means to an end. And so those software and user interface issues are really important. When I was at Microsoft, I spent a great deal of time working with the community and science on exactly those issues. How do we bring the power of advanced computing into small companies and into individuals' hands, where from their perspective, the ease of use that they find familiar in their mobile device or their PC extends seamlessly and apparently magically to exploit those advanced capabilities.
Great. Well, thank you. Thank you, Mr. Chair. This has been a great hearing. You know, I didn't pay enough attention to this stuff when I was in high school. I'm learning a heck of a lot now in Congress, and I could sit here for another few hours, but I know our witnesses and our panel have other places to be. But thank you again.
Thank you. Thank you. And I do want to thank each one of you for being here today on a very busy day in Capitol Hill. And with that, just want to thank you for your valuable testimony. And I want to thank the members for the questions that they've had. The members of the committee may have additional questions, especially with competing hearings that were going on at the same time. So we will ask if you would be willing to respond in writing to questions that we would submit. And with that thought, we will keep the record, will remain open for 2 weeks for additional comments and written questions for members and a request for your response to those. With that, again, want to thank you so much for your time and for your wisdom and information today. With that, the witnesses are excused and this hearing is adjourned. Thank you.